Wait a minute. What the heck kind of waveform is that supposed to be?
Hi, I'm Kevin. Welcome to my cave. It's been a while since the last video. Partly because I've been struggling with some domestic issues here at the cave, like plumbing and air conditioning malfunctions. But mostly because I've been struggling with my own mistakes.
Last time, we designed an amp that could use small signal transistors to deliver a watt of power into a resistive load that was about equal to a nominal speaker impedance. And it worked pretty well into the resistive load. The transistors got a little hot, but nothing that I couldn't hold with my fingers.
But we know that speakers aren't purely resistive loads. We can look at that in a little more detail right after this message. Before we continue, I ask you to indulge me for a brief public service announcement. Your support for the channel and its charities has been wonderful. I love you all. And so I know you'll respond to the call to take care of one another that I put at the end of every video. I've decided once again that my most recent payment from YouTube will go to the Against Malaria Foundation. The Foundation's sole mission is to provide insecticidal nets to people living in places where malaria is endemic. Its performance is outstanding among the charities that I've examined in terms of lives saved per dollar spent, to say nothing of the humanitarian and economic benefits of reducing disease burden in the tropical nations of the world. If you're inclined to fight bugs in more places than our circuits, I hope you'll join me in supporting this charity. There should be an affiliate link down there, or up there, or in any case somewhere nearby. Thank you so much for your generosity. And back to the video.
What a loudspeaker does is, of course, to vibrate the air. It does that by having a cone of paper or something similar that vibrates to push the air back and forth. To make the cone move, there's usually a permanent magnet behind it and a coil of wire mechanically bonded to the cone, forming an electromagnet. When current flows in one direction through the coil, the magnet and the electromagnet attract each other, and the coil is pulled in until the spring force on the cone balances the magnetic attraction. When current flows in the opposite direction, the magnet and the electromagnet repel one another, and the cone is pushed outward. An alternating current, of course, makes the speaker cone vibrate. But what we're looking at is a coil moving in a magnetic field. Motion of the coil induces a current in the coil that's proportional to the coil's velocity. This motion could come from the air surrounding the speaker. Every speaker is also a microphone. But it also means that the speaker affects itself. At very low frequencies, the effects of speaker motion can largely be ignored. The cone moves slowly in and out with the signal. The velocity is low enough that the induced currents are negligible. The reactance of the coil will also be negligible. All the driver will see is the resistance of the winding. At very high frequencies, the mechanical inertia of the speaker is what dominates. There's negligible motion again because the speaker cone barely has time to move before the signal reverses. Now what the driver circuit sees is the coil resistance in series with the coil inductance, and the reactance comes to dominate. In between, things get complicated. The principal thing that we have to think about is that the combination of voice coil and cone is essentially a mass on a spring. Give it a push, and it'll want to oscillate at a specific resonant frequency. The voice coil will contribute a current opposing the applied voltage when we drive it at that resonant frequency. A current opposing the applied voltage is of course a resistance. So at resonance, the speaker looks like a pure resistance, much higher than the resistance of the windings. At a frequency a little bit below resonance, the driving voltage runs out of phase with the opposing current. The net current into the speaker lags behind the voltage, which is the same thing as saying that the load is inductive. At a little above the resonant frequency, the driving voltage will also run out of phase with the opposing current. The net current into the speaker will lead the voltage, and the load will be capacitive. There are also other resonances about. One is the natural frequency of the motion of air in the cabinet. Speaker builders usually include passive radiators and often tune them so there's an acoustic resonance somewhere in the low frequencies to enhance the bass response. There are also frequencies of vibration of the cabinet itself, and even of the floor and the air in the room. Design of a speaker enclosure is something of a black art, and I won't get into it here.
When I got to this point in the discussion, I wanted to illustrate the effect with some actual speakers, and that's where I started just making mistake after mistake. Well, when I mess up, I fess up, so why don't I lead you through the rabbit hole that I fell into? I don't own an audio network analyzer, although I should maybe build one of these days. I think I could do a lot with a microcontroller, an I2S interface to both put audio out and read it back in, a power amp, and circuits to measure voltage and current. It could be used to characterize speakers, sweep filters, do distortion analysis, a whole bunch of things. So many projects, so little time. Anyway, for impedance measurements, you can use a function generator, an oscilloscope, and a tiny test rig. So that's what I tried to set up.
I cobbled together a test harness like this. The schematic is on the project GitHub. Link in the description. It starts with an op-amp to scale the input voltage, provide a low impedance source, and allow for a feedback loop. In the middle, there's a push-pull pair of emitter followers, with a resistor between the base and the emitter to limit the crossover distortion. We showed this configuration last time.
Future Kevin here. We did indeed show that configuration, and then we showed what was wrong with it. And I walked right into the same trap because past Kevin wasn't thinking clearly.
The test harness drives the speaker through a 1 ohm resistor, whose purpose is to measure the current. The voltage difference across the resistor is read out by a special purpose amplifier called an instrumentation amplifier, which is a programmable gain differential amp with very low offset voltage and very high common mode rejection, so it can read out a tiny voltage difference riding on top of a big signal. I've programmed the amp for a gain of 100, so that a 10 milliamp current into the load will read out as a 1 volt signal. The whole thing is surrounded by a feedback network, so the overall circuit has a voltage gain of 1/10. That lets me run the function generator with a convenient amplitude of a volt or so, making my struggles with noise a lot less, while still driving the speaker with just a fraction of a volt. The circuit had a nasty tendency to oscillate with a capacitive load, so I added extra frequency compensation at the op-amp. The transition frequency is about 265 kHz, well above the audio range and well below the frequency of oscillation. Using this little circuit, I was able to use the oscilloscope cursors to measure the time delay between zero crossings and the amplitude of the current. The calculation of the complex impedance is straightforward from that. And then I remembered that I can set up my digital scope to read out the phase difference directly. That was at least a little easier. But it wasn't really all that much faster. The phase is really jittery, so I needed to average multiple measurements. After some spelunking in the menus, I found the averaging function. Each measurement then took a while for the average to settle to a stable value. In the end, I wasn't sure I trusted the numbers I got. Instead, I decided to save the waveforms to files and coded up a program to measure the phase. After all, one of my degrees is in computer science. I'm supposed to know how to do that stuff. It says so, right on my shirt. And I ground through the data collection for one speaker. It was an incredibly tedious process. But eventually I had a whole pile of waveforms to transfer off the scope onto my computer. Once we have a saved waveform, the first thing that the program has to do is simply to read the waveforms that the oscilloscope has saved. One, here shown in yellow at the bottom, corresponding to the voltage across the speaker, and the other, shown in red at the top, corresponding to the current through it. They're both pretty noisy, mostly from the quantization error of the scope. Once we have the waveforms in memory, the next step is to determine the phase difference between them. I chose to do that by using a library routine that computes the correlation between the waveforms as a function of time. You can think of that in terms of sweeping the voltage curve along the time axis and comparing it with the current curve. The correlation at each time point measures how similar the two curves are. At a point where they resemble each other closely, the correlation takes on a high positive value. At a point where they are nearly the inverses of one another, the correlation takes on a high negative value. The point where the correlation is maximized gives us the phase difference between voltage and current. It's worth noting that nearly all the noise in the input signals is removed from the correlation function, because it is computed from all the data in the interval. With the two waveforms aligned, we can now produce a scatter plot of observed voltages and currents, taking out the phase shift. We expect it to be a rather noisy straight line. But of course, we can denoise it by fitting a straight line to the point cloud. The slope of the line is the magnitude of the speaker impedance. Since we have magnitude and phase, we have the complex impedance of the speaker, at a single frequency, of course. But compared with what we just discussed, it's not difficult at all to make the program suck in all the saved waveforms and plot the impedance as a function of frequency. And once all that was working, I completely ignored the problem with curves that was right in front of my eyes. I was too eager to take the data for a few more speakers. But did I want to use the same tedious process? Nope. Larry Wall, the inventor of the Perl programming language, once observed that 3 key characteristics of a computer geek are laziness, impatience, and hubris. Laziness. I was going to have to sit there for hours tweaking knobs, saving waveforms, and running the analysis. Well, it at least avoids adjusting scope cursors while squinting at the screen. Impatience. I wanted to get on with making the video. Plus, I know that if I do keep at it for hours, I'm going to skip steps, record wrong frequencies, save one waveform over top of another, and so on. My computer can keep track of all that better than I can. It's being lazy. That annoys me. And hubris. I can code this up in less time than it will take me to run all the tests I want to do. Right? Right? I mean, what can go wrong? Well, actually, not much did go wrong with that part of the process. It took me less than an hour to debug, mostly because I built the automation from bits and pieces of code that I had lying around from other projects. After that, the data collection was just ticking away. Literally ticking. There was a relay clicking in the scope every time that the data acquisition started and stopped, and the speaker was droning away. At least I could walk away while the test was running. I didn't need to listen to it. I went and collected the curves for a bunch of speakers, and only then did I actually look at the results. And they were garbage. At the high frequency end, they show the resistance falling off to almost nothing when it should increase because of eddy currents and core losses. In fact, for one speaker that I tried, the program failed because the resistive component was calculated as being negative. It couldn't be plotted on the logarithmic axis. After beating my head against the wall for quite a while trying to find the bug in the code, I did what I should have done in the first place. I put in an 8.2 ohm resistor as a dummy load in place of the speaker, and looked at the high-frequency waveforms on the oscilloscope. Oh boy, was that a mess! The trace of voltage going into the speaker is nothing at all like a sine wave, but it looks a lot like the sort of trace we saw when an op-amp's slew rate wasn't fast enough to keep up with the demands of an emitter-follower pair, even with a base-to-emitter resistor helping. So I started thinking what to do about that. And only then did it occur to me, we just built an amp that doesn't have that problem. I still have it sitting on a breadboard. And even with a bad load, I shouldn't cook any components if I limit it to tiny voltages and currents. Why not just add the current monitoring to it? And that's what I did. I added a 1 ohm sense resistor and wired the instrumentation amp to it to read out the output current. There was plenty of room on the breadboard for the sense amp. This time I was sensible enough to start by measuring the current using the 8.2 ohm resistor as a dummy load. The scope trace looked okay, so I ran a frequency sweep. The results were still disappointing. The magnitude of the impedance was now flat at 8.2 ohms or so as expected. But the phase angle was still shifting a little bit into the inductive region at high audio frequencies. It's not as bad as it was, about 12 degrees instead of nearly 90 degrees. But it should be very close to zero. I expect the resistors will be slightly inductive, but that shouldn't be detectable until we're up in radio frequencies. I must have messed up something else. Then I looked back up at the scope screen and noticed that the phase shift was real, not just a software artifact. And I suddenly realized what was going on. Like a lot of instrumentation amps, the INA823 that I'm using to sense the output current isn't exactly the fastest amp in the world. It's optimized for other things: low noise, low input offset, and high common mode rejection. Speed isn't really a priority. It's delaying the signal that represents the current by a few microseconds. That's enough to account for the phase shifts that I'm seeing. After a while thinking about it, I realized what I needed to do was to measure the voltage with an identical instrumentation amp. I also replaced the current sense resistor, so that I could even program both instrumentation amps with identical gain. That way, they should delay the phase by nearly equal amounts. The changes to the breadboard circuit were straightforward. I added the voltage sense amp and changed the value of the sense resistor and the gain setting resistor on the current sense amp. I then ran another frequency sweep using the dummy load. And finally, I got results that I trust. The impedance shows up as a flat 8.2 ohms across the whole frequency range, and the phase angle is 0 to within a small fraction of a degree. Matching the delays seems to have fixed the next to last bug. I think I can now run a frequency sweep with a real speaker. The magnitude of the impedance is showing the right sort of pattern, and the phase difference is also about right. It has 0 crossings where it's supposed to at the resonance peaks, and it gets an increasing phase difference as the frequency increases, although it's not as extreme as it was before. About a 47-degree phase difference at 20 kHz rather than nearly 90 degrees. But what about the resistive component? It's no longer falling off a cliff at the high frequency end. Instead, it's pretty flat up to a couple of kilohertz, even as the circuit is showing more and more phase shift. Only then does it climb slowly as eddy currents, core losses, and other nonlinear effects start to appear. This is now exactly what I expected to see.
And I think that's where I'll break off for now, so that I can get this video out. Between now and next time, I'll be characterizing my speakers again, and I'll save all the results for the next episode. Perhaps you'll want to inform the YouTube algorithm that you want to see it? I'm hoping that the next episode can also cover what happens to the amp when the load is reactive, which is what I'd have covered in this episode if I hadn't fallen into making caveman mistakes yet again. So until next time, stay safe, stay healthy, stay curious, and please take care of one another. Bye!